So hello, good afternoon. I believe it's Friday, and see where we are today. We'll do a bit of game design today. Game design, game development, interchangeable terms sometimes, but today is going to be more focused on game design, and by that I mean we are going to define the mechanics, the inner workings of certain systems in the game. Let's show what I mean. Fast forward the time to a morning hour, 6 o'clock. When we are looking at a compost unit, right now, this compost unit has some green material. As we can see, actually it has only green material. Because last time I was running this, I added I think a carrot into this pile. It is counted towards green material in this scale. So it is not balanced with the brown material. We'll work out systems like this. The relationship with the water indicator, and maybe temperature and maybe oxygen too. So today I want to work on a series of equations that will basically define whether this pile is decomposing or not. We'll take into account if the lid is open or closed, which will change the temperature. It may get too hot, or maybe it's not getting enough oxygen. Of course, if the lid is closed and it's raining, then the water content will not increase. Hello, Rectum of Justice. How are you today? Today is a normal dev stream, so it won't be short, just like this time. So I'll try to work out the equations and the mechanics, which is going to be interesting because it's easier to do this sometimes on paper, but I'll do my best to use digital tools to maybe work on some decay function. Let's find a decay function definition. At least I was collecting some. Function and decay. So let's see if this tool that I'm using is going to accept this, or will define this. It does. I think we have to do the power here. It's X. So we'll add a slider for A, and in this case, Y is the normal Y and X axis. So it's smart enough to know. But A and B could be. Glad you are doing fine. So thinking of the time difference, it's Friday, 8:30, I think. So I hope you had a good week. See this function and b. A and b is 1, this is 0, therefore it's always going to be 0. Let's increment a. Nothing happens because when b is 1, it's still going to be 0. So b, at least b has to be anything but 1. I think, yeah, we have some result here. Yeah, when b is less than 1, you have positive values, and power to x. Yes, that's the right way of seeing. As x is incrementing or is increasing, 1 minus b, which is 0.3. The y value will get smaller and smaller as you see that. A is 3.5. So changing a in the positive until it's 0 is actually kind of pushing the start point. So you need this to start sort of like as a is increasing going to the infinite, your this is the intersection here, say 5 and it's 10. Which makes sense because this is 5, this is 5. There comes a point that y is equal to for a certain x. It's always fun to figure out. Yep. So it's going to be interesting, challenging. Few things working together. A lot of is if else blocks, I bet, because we have major if else with the lid open or closed, and then we have the two major factors here, green and brown material, and then a combination of other three elements here to see if the compost is doing its thing. Or see. It is safe to say that let's have an arbitrary value. If this balance is more than 10% off, meaning if you have 60% green material, that is still okay. If you have 40% green material, that's also okay too. Either way, the other party will have either like 40 or 60%, that's still okay. The most ideal case is 50-50, but if you're off by 10%, I think we will still consider that as an okay case. Anything, I suppose the difference between two quantities, if it's more than 20%, that's what it comes down to, then there is too much uh, of the other value that the composting won't have, or the composition won't have. Do it that way. So let's write some basic rule here. So brown to green ratio um, sentence will probably have a bunch of grammatical changes. At most 20%. Must not be more than 20% different. We'll give examples. If 40% to 60%, it's okay, but 39, 51% is not. That's, we could check for this. Number 2. Actually, if I'm writing this here, I may as well write this. This is just a discussion thing. I'm going to create an issue. Regarding composting. Status of a compost unit. I need to know if my compost unit is finished with decomposing stuff. Okay, so this will be determined as a result of our equation. Lid. Ultrinium compost unit. Okay, I think we'll expand. There's one. One is satisfied. Does it we need a flow chart? Because if one is not satisfied, what happens? The state will be stagnant. How do I create flow chart? Um, could use Miro, Hero, depending on this where you're coming from, language flavor. I think flowchart is the safe way to go. Start is start. Brown green material ratio. Decision point. 20% apart. If it's yes, then it's bad. Then status stagnant. Let's write it this way so that there are less S's. If it's not more than 20% apart, there is a good ratio. Then we can move on to there's enough moisture. Um, sure, man. Take care. So how do you put that in a flow chart? I think I will simplify this by saying that for every unit or percentage of green material we have, let me give you a bit of background story there. So you gotta keep the compost pile moist. If it's too wet, then it's not good. Too dry, it's not good either. Let me just describe what is actually happening. When you put green stuff, you're adding nitrogen. When you add brown stuff, you're adding carbon. When you're adding water, you're essentially adding this, this. Uh, and also, think about this. When you add water, you are adding 2 times hydrogen than oxygen. So sometimes you need to tumble the compost pile, so you are actually adding extra oxygen. This way they are balanced. And maybe you actually should put twice the amount here. In essence, all these four elements boil down to this magic four elements. So these four elements are basically, what is that expression? What makes life? So you use these four elements in a certain combination to make everything. So when you're adding green stuff, which is full of nitrogen, part of that green stuff, you're adding grass clippings or green leaves, essentially wet garden stuff. That still carries some water. When you're adding too much carbon, dry stuff like newspaper, cardboard box, that's actually full of carbon. It no longer has the nitrogen left because it's been processed. Uh, that actually will bring, if anything, less water content compost. I guess the main difference is like when bread has, even bread has some moisture, but you know that when you eat soup, you're actually eating something more liquid than bread, but even bread has moisture. So carbon here is like bread. So there's very little moisture compared to, say, soup. Again, analogy wise, this is green garden stuff, say fresh looking. Okay. And this is going to be like cardboard newspaper that actually has high carbon content. So when we add these two things, we should still change the value of this in here. Um, but we may actually make a drastic change and say, well, when we add N, we're increasing H2O, but when we add carbon, we're actually taking away from H2O. So this is going to fluctuate based on what you are doing, proportions here. I don't think we can say the same thing for oxygen because adding material into a compost pile, why should it change value? It's not, but if anything, it's going to decrease it. And here's the reason why. As you are increasing your pile, there's less chance for oxygen to penetrate. So eventually, the middle inner parts will get hot with the decomposition. Uh, One of those things that they say, like in a ant hill, the center is actually really hot, or like beehive, and then bees try to get to the outer edges to cool down. So there's kind of like rotation. So they actually take. So that's why you have to tumble the compost to bring the oxygen into the center. So as the fullness is going up, will most likely increase the oxygen. So to compensate, we have this tumble or the stir action. So when the fullness is high, you are going to be able to oxygen. How much? Uh, that is the problem. We are trying to find a way to quantify this. Now, it is challenging to quantify water, oxygen, and temperature um, because they kind of need to be done in a unit. There is going to be a certain number of, how can I say that properly? You know, when you say five, well, five what? Five, what is the unit? What is actually happening? Like, is it five times? Is it like 5%? When you're dealing with ground and brown, green and brown material, that's okay to compare the area. The way we worked out this component is only taking into account the area. But say for 1 kilogram of green material, what does it actually mean in terms of water, oxygen, and temperature? That's the part I'm talking about. It's hard to figure out the quantities and units. But this is actually maybe a good start here. This x here is essentially time. This t is time. This y is basically whatever it is that we want to see. So it could be like, say, like oxygen. So if you want the oxygen level to be between 3 and 2, it is going to be between 3 and 2. Only it's between a certain time here. So I believe there is a way to change the scale of this so that it's more zoomed in, but nevertheless we understand. So when we say A is 5 or 10, it's actually doing this like 0, of course, it's so linear. So this is essentially going to be our maximum value. Because time will always be starting from a certain 0 point, but never going. So at any point, you could always find the 0 point and then going forward. So this A is essentially our highest value at a certain time. This has to be determined. But let's say we determined it as 5. Okay? Whatever that 5 actually means. And then incrementing B, or let's decrease it actually. Let's interpret that result. Let's go 0.5. This is essentially 0.5 power to t. Over time, as t is 5. That could mean like, I don't know, in terms of game time, maybe 5 hours. What we are trying to perfect here. So say t equals 5 hours. That means O is almost 0. So which means so if oxygen level is expected between these two numbers here, then we are way down here. So I think we could take some examples here. Say every 3 days. I think that's a good number. That's what I remember from. So when t is, let's assume t is actually number of hours. So when t is 72, it should be 0. Here we are quickly approaching 0 after 5. It's too low here. Um, And let's pretend that oxygen level is actually sort of done in percentage. It's 100% oxygenated. Okay, I think the step is already 100. This. So when the again we now have to adjust B so that around 72 hours. I actually want to give some leeway to say 72 hours. You're kind of going below the danger zone. So let's give it another day, 4 hours ish. At 96 hours, you are actually hitting the bottom. So around 96 hours, O is going to be almost zero. So we need to pick B certain way. We could actually go a bit more size here. Let me see if we increase this. Going to do something. It's going the opposite way. Let's do precision work here. Let's say the steps are, and you could actually do maximum. Because when we do that step, it's still going to be 2 steps, right? Only maximum is this. Maximum is this. A bit more precise, but again, not too much. That's more like it. I think I kind of see where this is going. You actually do it? I think you kind of hit infinity. 1 over this then is just 100 like this. We'll maybe check against some kind of rule that it maxes out. We don't. So in the game, our let me think. If I'm actually making this depending on 2 factors instead of one. So as the game clock ticks, okay, which is in this case t, is going up. If I leave everything the same with these two values, when starting at a fully oxygenated state in in 30 hours, we'll go down to 40% oxygenation. Uh, I'd like to get that 25%. I would like to be here when it's around 72 hours. 572, more or less there. That's okay. So around 96 hours under dish. You're here. That's not too bad either. So in the first 24 hours, which is it's losing 40% of oxygen. This is a drastic drop. And in the last 40 hours, let's say like around here, there's a less steep decrease. So this, maybe we need this a bit. Okay, let's see if we could find other decay functions. I think we may actually come back to this, but description of this. I think I remember reading about this. Eventually, I left it here. This is exactly the same article. Let's go to good old Wikipedia. Solution to that equation and such. Life. We are not just in half. Exponential decay calculator. Let's try this other one. Here's time. Here's a lambda value, decay constant. So in essence, we actually define a different constant in our two different constants. Let's create another equation here. Let's say, let's call it decay equals e to the power minus some kind of constant. Let's call it c. Okay, over t. I mean, not over t, times t. Let's slider for c. It's, you could also have some kind of constant. Call it. We already use a, b, c. D is this. Call it n. Let's look here. So n0, initial quantity. Initial quantity is 100. We know that. Okay. We could actually hard code that as 100. We already know that. This could be actually 100. And we would expect it to be let's actually change this okay, because we are trying to create a different equation that follows similar rules, but how it goes to those end targets is going to be different. This is done easy. Decay constant will actually define this time. We already incorporated that. NT is the result that we are trying to put in the graph. So essentially, we need to define our constant, how much it decays. So C, when you increase C, because this is actually minus 100 over e to the power of ct, which means you're actually increasing the value of the denominator is essentially approaching 0, hence you're actually squeezing the line here. So this has to go low. So I actually think this is going to have similar to B, initially 1. I don't think this will ever be less than 0 because it doesn't make sense because it goes the other way around. Let's just do arbitrary 0 here. This is where we can actually do stuff. You see how these two actually look very similar. That same constant value B and C, 2%. D and O equations for the lines overlapping. So and maybe here. Maybe we should. So that doesn't matter. We come back to the same value. Because I bet if this is 3%, percent 2, they are going to over. I think here's the beauty of it. In the first one, I mean, we could have actually typed this. Doesn't matter. Set that. So here we depend on B. Here we depend on C. Still doesn't matter. Which one looks more elegant? I think the second one. Why? Because it starts with letter E. It's elegant. Kidding. But it looks simple. I believe if you want to introduce another factor, we'll do so soon. Let's move on. We did this equation only considering its own depletion rate. There's nothing else that is playing a role in the calculation of oxygen. So if there is anything else. Question number 1. When the user stirs the compost pile, what is actually happening in terms of equation? Perhaps we are temporarily adding something like plus 10%. And then if it is actually here, it's added 10%, it goes back to like 50%. Then it decays from 50%. Because at some point this equation will actually get 50%. Just that you are temporarily resetting it and get in, get in there, and then as it's going down, you kind of sort of you do it, create a bump here, and then it starts to decay from here to a low rate, And as you keep adding more and more, you're sort of shifting the depletion in time. Like it takes basically eventually longer to hit zero. So we could add a fixed percentage to the oxygenation time. I'm gonna grab some water and okay, this 100 to 0% makes sense. So there is still a bit of room here. It's, I don't know, you could still count the percentage here. 1 or 2% after 200 hours. 144 hours is actually 6 days. That's still it's still too low, but it's visible on the. And yeah, when you get here, you are going to be very like near the 0 point. So I think this equation checks out for oxygen. Let's think of cases where we can actually have oxygen added and removed. The addition is when we do the stirring. That's good. Um, I don't think. I mean, yeah, we want to give the most realistic farming experience here, but um, we should also balance the complexity too, so that there's not unnecessary complexity. Because the question I have in mind is, if your file gets really big, we'll already include the factor that it's going to take longer for you to store it because it's a bigger pile. But should its oxygen needs be higher when it's a bigger pile? Because as it is, this function has no room for taking into account how big the pile is. It is only always decaying, no matter how big the pile is. We think about that. I think I'll leave the oxygen like this, but I will introduce the pile volume into perhaps either the temperature or the moisture content. That's going to be interesting. Okay, let's leave this oxygen here. Maybe oxygen should actually, and this, just get rid of these two. Okay, I think that we have something good going on here. Let me check this value. I think this was 2%. Because isn't that what I said? 90, around 3 or 4 days, which is 72 to 96. It's the printer just behind me. I was surprised something else. So 25% is sure will be here around what 72 hours. So this is good, which means the interpretation of this is that at some point when we have 100% oxygen, every hour it's going to lose 2%. That's what this means. And wow, not in a linear way though, because when you do 50 hours, if it's losing 2% every hour, this should hit zero in 50 hours. But that's the beauty of this uh, equation. So that in 50 hours, you're actually around 37%. So let's do a water equation. Now the water equation, I think that will go by liter. Uh, Here's actually what I want to find out. In Wayfair website has cost unit. In fact, I may actually have visited a few. This, I believe, will go by volume. Here's the dimension. At some point, I think they are measured by the amount of content they may hold, or in the game will implement them. Now it's giving the dimensions. Of course, it has an hexagonal shape, so we could actually create. We could calculate the volume based on that, but maybe they are actually nice to give us volume posters. Our unit is like conditions. There you go. This is not meter cubes. Stupid. That's the liter. 340 liters. Okay. So this is what we'll put in the game. New page. So this is what I'm imagining. 340 liters compost. When we add material, we'll measure it by volume. Right now, everything we include in compost unit is by 15%. So maybe we'll change this into liter, and you'll see the liter. I mean, the fullness changes in terms of liter. So when we add green and brown, that will directly contribute to the volume change. So what I would like to do is fullness, and we could actually be silly about it and write it this way. Could actually have fullness in terms of brown and green material. This B is actually going to be this B. It's actually change. Uh, Depletion. So let's do this one D. Let's do D. Actually, since this has become a constant, so we'll actually do 2. That way, we actually don't even need anything silly. Still the same equation. It's good. Head slider for B and G. We're going to add. So B can only be 0. No maximum thing. I think it sort of be as a function. Classic f and g. Let's do a constant here. Let's do this one 0, 2. Okay. So like this way we'll quantify it. So f is determining the fullness. Okay. When you have 1 liter brown, 1 liter green material, so your f is 2 liters. Okay. Depending on how full your compost is, the water um, that is needed to keep the composting going will be determined such that W will depend on F. Um, Almost want to write it like let's go with the magical 2%. Welcome back. So just to recap for you, because I was just about to move the topic, but I've hit a breakthrough. So in this chart, O is displaying the oxygen. So at any point, you could actually have maximum 100% oxygenation each hour. For each increase in T value, we are using up 2% of the oxygen. So it will take us roughly, I don't know, 300 hours to hit 0. But the goal here is around 3 to 4 days. We are actually hitting the low threshold value, so that's good enough. Let's done. Then I moved on to calculating the water content. I was saying earlier, hitting N and C will change the requirement for water. How much water you need is kind of depending on how big the pile is. Fullness. Fullness is going to be defined by how much you D and G, brown and green materials. This is going to be liters. We have a model of compost here with 340 liters roughly. So we know that the water requirement will have to depend on if we pretend that every hour it's losing 2% of its water content. Just about to interpret this because here Because how do we measure this one? Decide to go with percentage as units for the oxygenation. But is water going to be based on liters? I mean, the player doesn't really need to know because all they are going to see is where the marker is. This is not even the final design. Final design is here. This one is going to change. They're all going to be horizontal version. The minimum and maximum will be defined as red zones and green zones, except this is going to be similar to this. Um, so when the bar is in the green zone, it's good. It's that. Go back to the equation and let's try something crazy. What if I have, say, let's just do extreme cases. If I have like, did you actually do almost perfect case? The case there is an equal amount of brown and gray. So in total, there is 158 liters uh, composting material. So it fits the container. That's all good. What happened to the water? This happened. So after 1 day or 2 days, oxygenation level is still in a good stage. I think this equation is not taking into account what I was saying here. But in simple terms, what I would like to incorporate is adding more green will help the water content. Adding more B will penalize the water. So we cannot do this F as a simple term. This actually has to be broken down as these are good, like real bees too. They're good. Can we this is B minus G? What this is supposed to be. Because this is what I'm thinking. If we add twice the brown material, sorry, if we have green materials, green material twice the amount of brown material, 40. Or not, or I thought of the right thing and said the wrong thing. Imagine this is actually adding some water. This is actually taking that water away. So eventually, the difference here is going to be 40. That's the 40 here. Now we may actually do this in a more exaggerated way. That every brown is going to take away 2 units of water. So then that would be 2B minus G. So we'll look into that. But let's also keep in mind that ENG can be maximum 340 in this imaginary unit. Um, because here's the problem with this equation. Let's imagine this person added 240 liters of green material. I think my equation is wrong. Green should be beneficial, brown should be. So, yeah, if anything, it's a 400 here for fuck's sake. Okay, everything checks out. So if we keep adding more green, 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 so we're increasing the water content. At some point, we are adding so much green material. And what does it even mean to 140? Like we know these are in liters. It's the difficult part, right? Never mind. With a proportion like this, it will be stagnant anyway. That will be fine. But displaying this uh, won't really depend whether it's stagnant or decreasing. Only this comes back to a normal state. This has to be in a right. So when I read about composting, one thing they say is, not too dry, not too. But how do you actually define that in terms of volume? How many liters of water will make a volume of compost pile wet? Let's say it's 1 to 1, but we'll still do that brown material taking away. Your total volume is B plus G. You have, in this case, 220 liters of compost pile. That seems too high though, 222. Now look at a pile, let's say, soccer ball or something like a bit bigger, maybe like chair. Shape is weird, but maybe we need 1 to 1. But because we are compensating when we add green, rising when we add B plus G, also change the order of this. Psychologically, this will make me feel better. Green brown, because green brown first, second, left, right, green, brown, minus. Okay. The way we built this component in this one, um, I see is the wrong one because I have the wrong thing pulled in. I need to be on branch. Anyway, we did this so that we could actually change minimum and maximum thresholds. So in this case, those thresholds will be depending on B plus G. So in the oxygen threshold, we had an arbitrary 100% oxygenation. For a volume-based equation, your highest value, therefore, this value here, or not necessarily this calculation here, but whatever the final value here will be, that will be based on total amount of volume. Now, we could actually simplify this by typing this, which kind of makes it sound like you can do nothing but add water to this compost unit. Kind of makes sense, but I mean, this particular unit has some considerable holes between the planks, so it won't actually contain the water. Because here, realistically, we are talking about stuff holding the water, but then we said that is actually essentially B plus G, which answers my question. So this maximum value is B plus G or G plus B. Okay, this will still come into play. So that's it. So for I'm still kind of formulating a real answer, but so far this is more promising. If you have this much green material and this much brown material, we said but no, we said green is helping, brown is penalizing. It still has to involve GNB. This part is actually okay. Calculation is kind of. I'm tempted to write it like this. It's going to be 1. Because I'm not thinking. Okay, let's imagine this. Let's imagine the most simple case where there is no bonus, there is no penalty. For each green and brown, when you add 1 unit of green, 1 unit of brown, you need 2 units of water. So that means without this, it make so it's the same shit. So we'll look at this thing, how much water content it has. We'll compare that according to this, and we'll say, hey, you need to actually have 222 liters of water inside you, whatever this material, this pile has to hold. But maybe you are here. We'll actually display that accordingly. Maybe somewhere. So that's the case without bonuses and penalties. Because you added G, okay, this number shouldn't be that high. This number should come down because you added G. So it actually should drive this down. And we could actually do it this way. For every G you add, maybe again a stupid ratio, maybe you kind of gain half back. Every G kind of counts too. And now you took one back, it is basically G. And for every B you have, you're actually taking a half away, so this is actually B over. Let's see if this makes sense in terms of numbers. Let's go with sweet numbers, 30, 60. Because, long week, it's Friday afternoon, brain is pelted. Looks like a sweet 70. Why is that? Under no bonus or penalty condition, we would actually be at 90. Okay? Because um, we added 60 liters of green, which actually should give us 30 liters of water content because of its moisture and whatever. We would not need 90 liters of water, we would need 60 liters of water. Okay? Sorry, I'm making a correction. This is 75. Because I already thought of the next line I'm going to say, which checks out. So now, because we added green, we dropped our necessity of water down to 60 liters of water. But because we also added 30 liters of brown, which is if it's sucking 15 liters of moisture, that means we need 15 liters more water content, pushes the requirements back to 75. However, although the math checks out in terms of display, the interpretation doesn't make sense. Uh, or does it? Because when I say 75, the math checks out. But in this graphic, 75 looks like the high threshold. Instead, that 75 should be it's as if this should be kind of somewhere here. Because this equation is not really answering the too much water problem, right? Really not. Guess I was gonna make this percent for calculation. It didn't matter. It's still 75%. Still our same old problem. Instead of 100, write something controversial. This is essentially 2G plus B. So it. That's it. Part of me wants to this part doesn't make sense. This does to a certain extent. This is thinking that you can only add as much water as the volume of the rain. This is going to hit 260 T is 0 for a case like this. Uh, then 20 plus this 180. Yeah. What's the interpretation? About 72 hours. About 72 hours. To put that, we hit zero. First, 0 liters of water. There's something kind of pleasant to look at this graphic. It makes some sense to me. Part that doesn't make much sense is they will be adding water. There will be rain every minute. Every 10 minutes of rain, maybe you'll be adding like, I don't know, 1 liters of water. 1 liter of water. Maximum of this, maybe. And this is the evaporation rate. Again, hard coded. Honestly, between these two equations, the orange one makes much more because it has a realistic start point, 340 liters capacity of the compost unit. Now, it's stupid that you are going to fill it all up with water. But if you did, then at least where it should start, which also means that if G and B are zero, um, that similar to the other equation, that its maximum point is essentially 340, which is the maximum amount of. Now, as this is going down, T, uh, where the interpretation must actually fit the model, or scientifically, the model should fit the observation, but let's at some point when we add more brown material, we this is where this part doesn't make, because as I'm adding more, well, okay, there are two aspects. Let me tell you this the stuff where when you're adding more brown material, see how quickly the water is depleted. Actually, more. Um, However, this initial point is kind of this part is making sense. But it takes fewer hours to get down to 0 liters because soaking up the water. You're increasing G. That's the part that also doesn't make sense. Well, it kind of does, but it's actually because you still need some water to compensate. But G increasing G doesn't actually do it this way. Doing this 100 is going to take it here. 96. Increasing this 100. Okay, there's clearly something wrong here. The model doesn't fit the interpretation or the observation because when you have the same amount of green and brown in a reverse way, in the green case when you have 100 over 0, or like the versus the 0 to 100, in the green case when you have more of that, it should have taken longer hours to hit the water. So although this drop off rate is actually making sense, it's steep, I get that, but the way these things are played out is wrong. um, and I think when I did this, it takes 300 hours to deplete itself when it's 100 liters of green. Let's take it down to brown. If anything, in terms of numbers here, yeah, there is still some confusion about either the interpretation or the equation there. Because why am I not doing it this way? Because if B is going to penalize, every time you add B, it sort of feels like it's 2B. And this equation is sort of like the water need. And this really has no bearing. And why are we even taking into account? Let's do a simple math. Okay. We actually have a case, right? We'll grab some chocolate to expedite the thought process. Let's say we have this case 100 liters of brown material just dumped in a compost pile. You should say if W is indicating the water need, it should result in 200 liters. Is it? It's most likely not. 100. Then maybe starting at that 100, we can talk about the decay. It just happens to be the same 100 here with the rate. So sorry, this actually should have been 200. Let's do this one. Okay, there you go. But here's the problem. When we use the decay function, and our interpretation of W is that the water need. Why should the water need change over time? That's, I think, what we should first decide on. In the case of oxygen, it was showing the oxygen content, not the need. So suddenly, for the water display, we start to talk about needs, but not the water amount. So that's what we should actually settle. I think what we have been working on here is this is actually calculating the minimum thresholds, not the actual amount, or a mix of two. Okay, writing it down. When we have G plus B, we need at least that much water as a beginning, sort of the low threshold value. An equal amount of water. But write that down. For the minimum, going to be something like maybe we'll do this half. The maximum water. 2 brown minus G, because that's the penalty, right? Maximum water. Okay, nothing is happening because G is 0. In this, okay, this kind of makes some sense to me. When you have what is this? 100 liters of brown. It's as if okay, let's actually answer it this way. Go back again to 60 to 40. When you have 100 liters of content in compost, because you have more of brown This pile will need a lot more water. In fact, what did we say? In normal conditions, this will actually need 100 liters. But because we are adding 40 liters of green material, let's consider half of that as extra. So this is we need now 80 liters of water. Then twice this G plus B plus, actually in this case we'll do like sorry, over 2 plus 2B. Okay, that's what we are trying to, plus 4B. That we need this here, take some of that, more of that, plus 4B. So 6B plus G. That's why it was, it's actually 6B. Something was way off. Let's see if this is actually flying the moon. 400. Suddenly everything seems to. Why is that? Oh, by the way, I should have actually halved this. Still going to, because when I did that, yeah, 400 was just real. Okay, let's approach it from this logic. G plus B, we need at least 100 liters because we added 60 liters of brown, which is more moisture to break down. We are assuming that for every brown we need double the amount of water to break it down. So we need an extra 120 liters of water. So that pushes it up to 220 liters. Then, because we have 40 liters of green, which then helps the water content, half the amount. So 40 divided by 2. So it's as if we are gaining some benefit of 20 liters. So that takes it from 220 to 200. So if this thing has 200 liters of water, it's good. And then to turn that number into a high threshold, we have to remember that the way we designed this is that this is actually the 25%. So if the that's where the confusion is. We are trying to convert this need into threshold, kind of fit that value in between a happy color here. Let's answer the question from a different point of view. It's as if, well, because so far we have answered this question. This 200 liters is what we need to have to break this down. In essence, this 200 liters is kind of the perfect scenario. Okay? So ideally, you should be in the middle. So then maybe this should be 100 liters. This should be 300 liters. And this being 100 liters is also making some sense from a primitive point of view. And that primitive point of view is this, the basic interpretation. When you have 40 liters of green and 60 liters of brown, you get these 100 liters of, that's the minimum. That kind of answers that question. This equation is still taking care of the drop rate. That's fine. But part of our job is to define the minimum and maximum values. Well, if this is 200 liters, this minimum will be 100. So that when you are getting to 150 liters, then you are entering the danger. And 200 liters being in the middle, here it's going to be 250, because maybe we'll do it like what, double, like equal share, like 200 here, 100 here, maybe going to be 250. Um, and then let's try to interpret that 200, like that 250 liters in terms of our material content. I suppose psychologically, when you have a pile of 100 liters and we decide that we should give double the amount of water, that's the ideal case based on this GNB. But 250 liters is like, trying to figure out that, like, they see this from the player's perspective too. Because I don't want people to feel like, oh shit, I just gave an extra liter of water and too sensitive, and now it's beyond, like, it's off charts. 50 liters feels like, wow, you have a lot of room to fuck up. That kind of makes sense. 100 liters is a big amount in terms of like pie. Which means let's actually decrease the pile. Take this down to 2, this one to 30. The pile is half the size. Let's interpret this. Now we are looking at yeah, let's cancel this black one. I think what we could do is what is G's? Could also do it this way. Let's try to synchronize these two. Close enough. One thing that is kind of bugging me here, it's as if time has no impact on how fast this file dries. As G and B are increasing, see that, but then again, we said this graph is not exactly presenting the water content. This is essentially what we are after. Um, this is like the high threshold. And the low threshold is G plus B. And stop this animation. And like, I think if I could incorporate that minimum value here, then we are done. I think that that is throwing me off. Because this is what I kind of want to feel. I may even introduce a factor here. The G and B are part of this equation, but this is not the final form of the equation. This, when the time goes to infinity, will eventually hit zero. That is the case with the O function here, oxygen level. Because the way we determined the oxygen measurement by percentage, that we said it can only be 100% or 0%. That was an arbitrary choice that we said whatever. Okay. At that point, I was discussing whether the pile volume should play a role in this, and we said fuck it. But with the water content, our decision is deliberately on making the pile volume be part of this water threshold. And we are confused about the need versus the measurement of it. But whatever the measurement will be done against the minimum and maximum values. So if we are determining the minimum and maximum values by the volume, which involves G and B, so we should determine a maximum G and B and a minimum G and B that will be part of this W function, so that when t goes to infinity, the minimum value of this W will be the minimum value that incorporates G and B. So, but when we say, well, you should have at least G and B, say this, well, then this will go to 100 and stop there. Now, that's where the things are getting kind of crazy with the interpretation again. But that is kind of going along what we were saying before, I think. When we want to make this, we said 200 is here, right? And we said this should be 0, this should be 100, not 0. Because we put this 100 here, this is actually also, this equation is also giving us a thread, just like the oxygen one does. By the way, because oxygen feels more like blue, it's fucking blue now. Anyway, water is also blue. This oxygen. Anyway, so this is okay. Okay. 200 here is at maximum it should be, why is this 300? Because that also makes sense. When it's in the middle, we said 250 is sort of like, well, you've added enough water, like 50 liters more. Come on, like you're saying there's enough room for fuck up. If you add more than 50 liters and get to 300 liters, you overwatered it. What is this? Swimming pool? Compost unit. Too much water. So this whole equation is essentially doing that. I guess we are done here. So let's take this, stick it here. Okay. We need at least this much water. And at most it could be this. And then over time, it's going to, you know, dry out, dry out, dry out. Now let's see you guys. You. Also, these two values are extremely high. So let's make 50, 50. If is this. Let's have a friendly scenario. We have 6 liters of green and 4 liters of brown. Just want to interpret some stuff here. So 25 is maximum. Because I've been always favoring B over G. This result is throwing me off. Math checked out. The maximum value when it's for green. I need minimum 10. That's satisfied? I think it is. It's actually approaching 10. That's guaranteed. Because I needed at least 10. Edit 4 brown. So I need actually 8 more water. 18. But because we have 6 green, so I should actually take away uh, 3. So it should be 15. Why is this 25? Fuck, man. How did the math checked out before and yet it doesn't now? Need at least 20. That's okay. It's approaching 20. This is actually handled. That's maximum threshold. I thought I had that. Now what? So I need 20 plus double the B minus half the G. 35. Here we are saying T is okay because before I was not. Yeah, see, when I edit this to set the minimum, part of this already is in here. This now seems too high. That is already incorporated in here. So so this is kind of going back to our original. You need where I turn it into. It kind of checks out though, because didn't I say 35? Because the minimum will always be 25. I mean, 20 in this case, can be. And then I said when you have 10, 10, fine. For the 10 from B, you need another 20. So that's like 40. But then minus the half the G, which is 35, which actually brings it down to 30. Right? 10, 10 is 20. There's 20 from Brown. Okay, what is this here? Yeah. So another 20 from Brown, so 40. But minus half G, 35, and yet this is the, oh, I have to half the G. I keep staring at the screen and it's only decreasing 10 instead of 5. It should be this, so it's 35. So the math checks out in my mind. This is a horrible function. This actually should be 4b minus 2g over 2, which is more ridiculous. This way, so you're here, and then way. Okay. That's what it is. So it still takes roughly 3 days to come from 35 to maximum to something. Let's do this 200 Ks again because I think my it's set to. Okay. We should hit the magical 200. That is actually good. We decided that the 200 is actually. So whatever value we have here, this two, the, so this is the. So in 3 days, right here, 125 liters. It drops down to 125 liters. It starts at 200 liters. Which is okay, considering the minimum should be 100 liters. So the last 25% is going to be. Kind of, no, it doesn't. Well, it does according to this scale, but I was thinking the maximum should be 300 because 200 is the happy, the middle case. So if it's going to drop from 300 to 125, this is actually below 25. This is actually 12.5%. I think my current confusion is I think I'm making a fundamental mistake here. When I'm calculating the maximum amount, I kind of tend to merge these two things together. However, there are two distinct parts of the equation because this part doesn't apply to this part. This is a necessary evil, so now we need at least the minimum amount of water in terms of like just the bare minimum content, 100 liters. Okay, that's what this part satisfies. This, on the other hand, this should actually be such that when t is 0, altogether, when this is 100, this should result in 200. They should push it to 300. Kind of the problem, though, now that is actually correct. Um, Again, the confusion in this equation and the graph and the whole design here, visual design too, that there is a mix between the need and K, also meaning consumption. Now the player actually may see this combination. Well, they actually need, in an ideal scenario, 200 liters of water. Let's imagine this is for water, okay? For 40 liters of green and 60 liters of brown, they need 200 liters of water. Um, and that would be the most perfect case. Now, starting at 200 liters, given enough time, it's going to go down to 100 liters. That's what this is showing. However, although these two parts are giving us the perfect scenario, we can always easily do the minimum scenario by just simple math. This equation doesn't exactly give us the 300 liters. It should be the maximum here. That's where I kind of confuse myself because I want to see 300 here in the results, hoping that I would actually go from maximum to minimum value, but not exactly start point. I kind of look at this as my start point, which is throwing me off. Okay, so I think I'll write few notes here and there for the generic way of calculating minimum and maximum thresholds, because the decay part kind of works. Because the decay part will essentially be this. We won't actually have any of this. Decay part will be, well, what is the current value content, and then at another t time, what is the new water level. Okay, for water, threshold minimum equation is, can we write comments here? This is actually the minimum, PNG. Threshold minimum for water is PNG. Let's decide on that. That's the maximum is, we said B plus G, and then we need 2B, but then we also need minus G over 2. Then comes to 2B, 2G, 2B minus G over 2, okay, which is 4B plus G over 2, okay, that's the maximum. And I think that's really where things are kind of off. It's for what? 4B plus G, go away, the maximum. And I did the math again wrong. Oh boy, old brain. Where we had actually 6, which we were happy with from before. Six B plus G over 2. That's what it is. That's the black one. Just 200. Is it even true? Punching numbers. Still something is not quite right. I think I should create a separate function because I'm going to keep confusing myself. Can we actually create a different? I'll know what I want when I see it. Um, I don't even know the name in English. Forgot the name in French too. We learned all this in French. But when you want to talk about like X, but X1, X2, how can you even Google that? You can just say different X's. Mathematical X symbol, X algebra symbol list, like X1, X2, that kind of thing. How do you even actually talk about that? I didn't actually even see it here, but it's hidden somewhere in the menus. Like this sort of logarithm, like the A, the base A. Basic. It's not gonna. Yeah, but what is the name? It's just specific things here. I mean, even this might do. It's silly, but did I see derivative? This is a derivative, but not the symbol. ABC. Gotcha. Okay. Delete yourself. Calm down. You need to type something. I'll do water minimum. Okay. Um, water low should be this. Is the threshold. I want to create another one of this. Is going to be water threshold high equals. That's what we need to do. Okay. Forget about this for now. Get to that. Move yourself up here. Smarten up. So the equation is this. It should be at least this. Okay. Can we, by the way, map this out? Why can't we do that? Oh, just call UI interfering with this station. I thought there was a way to turn this expression. There is the expression. This is static expression, like just 5. Just do me a graph. It's 5. Forget that. Folder image. Can we at least do this? Let's see. Let's do the F. Subscripts cannot be empty. Try adding Y to the beginning of. Okay. This is allowed. The other one is not allowed. Do something. Water content low. I need to learn the tool too. Okay, I'll do it this way so that no matter what the x is, and in this case, I think this could be t. Um, as time goes on, the threshold of the minimum threshold for compost unit will be minimum PNG. Done. Take this, put it here. This T is gonna go up. Now this is the low. We did the low. Let's do the high. Okay, still going to be T, and it's going to be at least this. Okay, plus 2b minus g over 2. Let's simplify. Is a function, try using parentheses. Let's also say fuck here. I'm doing it this way. Okay, and you are do you black. Okay, this is something. Okay, forget this. All good. Now I think this is where I was saying this should not be 200. This should be 300. That's what we'll fix here. The water threshold high value with this kind of content should give us 300. That's where we actually have the math wrong. Then whatever the water content is, it may decay following this. Anything in between those, this two, that's fine. So why am I not getting 300 here is because I need at least this much, but plus double the B, which is good. This is actually helping us. What is the problem? 100 and checks out is 200. I think maybe it is actually 200. I always thought 200 was supposed to be the ideal case. When you have a pile of 100 liters, so it is really 60 plus G over 2. Let's turn this on. Let's try to replace this with this. Do this. It's going to fuck it up. Do it this way. Okay, at least we are replacing the for the functions. Save. So this looks like the player just gave maximum amount of water. So the high threshold is 200, the minimum is 100. Player just flooded the compost unit. It is just at 200 liters. And then if the player doesn't give any more water in roughly 72 hours, it's going to be below 25% that threshold. So this is actually good. If the player actually gives um, somewhere, we can actually do arbitrary number, say 50 liters. Okay. Um, the magic number here is 125. That's what I want to see. Because the threshold will be the same, 200 and 100. Danger zone, the green to red transition will be around 125 liters. But compared to 72 hours to get to this level, you are going to need 33 hours to get to this scary zone, which makes sense because you are starting with less water content. You're starting with 150 liters of content instead of 200. So of course, when you have more stuff, it will take longer to evaporate. So this actually checks out. So when you have even less water, let's say you have added 25 liters of water, the danger zone, remember, is again around 125. Um, well, in this case, you are already kind of there. You are really pushing it. Yeah, the 25 that is kind of like, well, you had you're at the bare minimum. The way these numbers kind of work out right now is that, well, when for 100 liter liters content, you kind of need 25% more liter water. Um, I think this checks out. When you do 75, of course, it's like this. Problem isn't going to be if you're approaching the high or the low, but that if you're in that area, you're not decomposing anyway, so you are penalized. So it's not always about adding more, because you are interrupting the chemical decomposition there, the reaction. But it makes sense that if you are starting at a higher value, that it's going to take longer to get to this number here. Yeah, like this. This is just a high number by virtue of working out the bit. I mean, if you really want to add like another, I don't know, 100 liters of water, well, which is actually where we are, like say 50, which is stupid because you need to be uh, below 175 to start the decomposition. You need to be here. Okay? You need at least 34 hours to get to the happy zone. Okay, but if you pushed your luck, you still overwatered it, you will need 14 hours to get there. So yeah, it makes sense. And with 75, you are just about to enter the red zone here, because this area this area is essentially this area and this area, or in the vertical case here, this cases. So in this case, well, you are right there. You don't need to spend any time to closing. You're already in the green zone here. And anything below this 5, you're always in the, only when you approach 25 and below, then you're entering the red zone. And of course, the less water you have, the more time it, of course, well, at that point, it doesn't matter, like the way we were doing about the threshold. Things are fucked up, and here it's too dry. Nothing's. I think we have a winner. This is, of course, this is just a punching numbers. Like this could have been anything here. This could have been just this. Doesn't matter. This value is going to be our current water content, and this is like every t we are feeding new y value, and then that new y value is actually coming here. So then every hour we are taking 2%, and even this is sort of arbitrary, but these two, I think we are okay. Let's recap this for my sake. So we have come up with two equations. One is the minimum and the other one is the maximum water threshold. They are calculated based on the number of the volume of the green and the brown material this compost units. The more you increase the volume, the more water content you will need. However, the way green and brown materials work and need water, uh, their proportion will also play a role in the way we determine the minimum and maximum water threshold values. That's this. Separate from that, starting with an amount of water that you have in this compost unit. Let's call it like moisture. Okay? By evaporation, it's actually gonna taken away. Um, the only thing that is perhaps not logical here is this is why I'm not so quite happy with this, because then it doesn't have any moving parts. These two functions is, imagine this scenario. You have this scenario where you 40 liters of green material, 60. The water content is 150. Just perfect. You just dumped 50 liters of brown material. Suddenly your minimum will be 50. Kind of checking out actually in my mind. Okay. And your maximum will be 60 plus 47, 350. 150, this is 350. 60, 350, yes, 350. Because you dump so much brown material. This gap has grown. What it was 100, 200 to 100. Adding just 50 liters of brown material pushed the gap to 200. Which makes sense because it actually requires double the amount of water. And even that could be a factor in the game. And then the player said, you know what? I'm doing something really stupid. I'm going to dump, I don't know, 50 liters of green material. Hear this. Arbitrary number. Now the minimum is going up first 50 more, which is 200. And this is gonna go up to 375. So it is not drastically changing the upper threshold. But I suppose the benefit there is if you only had like this, after adding that much brown material, when you said, "Holy shit, I don't have enough water. I just want to add 100 more liters of water," so you just went back up to like 250. Said smarten up and add at least 50 liters of green, you are still not too far off. Still in that happy zone. Because green material actually is helping you. That's the whole idea. So in a sense, yeah, GMB is still playing a role in this. Well, not directly, but at least the amount you have is not seen as atrocious as it might be, or it's not the end of the world. And actually, if you increase B, then it is the worst case scenario. But if you add G, at least your existing value is compensated. Let's pull these values into more human values, because human beings shouldn't actually have things, I don't know, more than a few liters. What are you doing? Okay, that's that. I'm actually happy with that. Let's remove that. This Y is essentially your water consumption, therefore I'll change the water. So that's, now we'll actually have more fun cases here, because now water doesn't have any correlation with oxygen. And when it's raining and the lid is open, we are essentially adding, could we incorporate that? Because I want to utilize these functions directly in Godot. Say we are not changing BNG, but it's raining. And if it wasn't raining, increasing T, meaning spending time, would take away 2 liters of water the hour. It's too high, maybe it's too low, I don't know. But we should actually, let's look at our design notes. Something, some issues. I think that might have been a discussion. Smartening up. Rain. For every minute of rain in the game, add 1 liter water to, okay, increase water content of compost. So half a liter, if half a liter every minute. For now. We'll get into other fancy calculation stuff, like say if the surface area of, thing is large or whatever. Half a liter per every minute. That's too much. Maybe every hour. T is defined as hour. The world here. So we are doing zero point 0.5 T. Okay. This is a conditional case though. This is only happening when it's raining. Because this doesn't make sense. Like, I mean, the only reason why this makes sense is somewhat like, showing it this way. Can we do if cases here? Am I really pushing the silliness? Desmos. Desmos if statement. We might actually have something. If then else has command structures. Using conditionals to is one. I suppose I could have it as a boolean. R equals 0 or 1. 0 is nor in. R. The if then else are separated by colon. Sure, but in this case it doesn't make sense. You kind of need a boolean. That's really what it is. Boolean function. Doesn't really apply to my case. I think I'll do it with the basic range. Say something like this. R is 0. Double check again. There's something like a checkbox. Actually more here. Click this. Well, maybe someone smarter than me knows and will, but I'll just say R can only be either 0 or 1. Step is going to be, because otherwise it does that. And this is actually when when it's not raining, your let's also do this 0 here so it's easier. When you have 150 liters of water in the compost unit, we said in about 9 hours you're entering the danger zone. Okay. But when it's raining, you're entering the danger zone in another 2 hours. Is good. However, at some point this is interesting. The math doesn't lie. So evaporation. Every hour you are taking 2 liters, like the 2 liters, is it? It is kind of, yeah. You're taking 2 liters away. Well, this kind of made sense with the oxygen, but here we interpret it as 2 liters. It doesn't make sense because this is the liters. This is the liters, half a liter, 150. This is like then 20 milliliters. We'll make some story about it. That's fine. But the moral of the story here, or the graphics, is that as it's raining more, around like, I don't know, 85 hours of rain, there is evaporation, sure, but after that, good luck. This compost unit will keep filling up slowly but surely. Uh, Around like what, 360 hours, you'll get to the danger zone in the upper limits here. I think everything is kind of making sense here. Well, this is an arbitrary number, but this now maybe needs to be played. So let's not rain. Not rain. So at some point when you have 150 liters of water, in 20 hours you evaporate 50 liters of water. So every hour you take away 2.5 liters. And another 20 hours go by, go to 40 hours. Like this, I'm zooming in. Then it's 67. So in the first 20 hours, when we lost 50 liters of water, the second 20 hours, we have only lost 33 liters of water. So our evaporation rate has slowed down. And because our rate is slowing down as time goes by, but when it's raining, you're always adding more constantly. Um, that is really not depending on, don't have diminishing returns. So, which means at some point, the evaporation is compensated by rain, and then rain takes over, and then you happy scenario here. I mean, you still need to water your compost. Here in 11 hours, you need to water your compost, and it's unlikely that you'll have rain in 11. This is helpful. However, not that much help. Perhaps it could be made more helpful. That's when we'll play with this stuff. Now, question though, should we really use this decay function for water evaporation? Because this makes sort of sense when it's raining or not raining. Like even when it's not raining, because you have diminishing returns. The longer time The longer the time, the less evaporation you have. It's taking kind of longer to evaporate the whole mass. But isn't that the opposite thing that like you have, I don't know, what is the science of it? Water evaporation rate. Someone has actually answered that question. And also I know that it depends on temperature as well, which we'll take into account soon. So this equation will get even more crazy. And also will include this factor, whether the lid is closed or not. Okay? Because it will also actually have this. Let's actually do that. This is going to have lid is either closed or not. 0 or 1. Okay? This is going to be here. And this is actually going to have lid. It might be raining, but nothing will happen. Only if the lid is open, it's going to actually receive a lid. That part is done. We could also do the lid doing something with temperature when we add the temperature. So, see, evaporation rates are usually over 316. Something fishy about this. Where is the page? Because the time of the year and whatever. Could this page be displayed in a more 'This is of course millimeter, like there's some surface area there. This is, yeah, this is the depth surface. So when you say 2 millimeters, uh, you have to calculate the volume because we um, so if this is the example, hundred and fifty. This is actually 1500 millimeters times this 3000 cubic millimeters, which is okay. Interesting. Yeah, multiply the water surface area, which I did. So yeah, here's an example. But here's the thing, this takes into account the surface like this. As I was saying, the larger the surface, the bigger the evaporation might be, which then changes this evaporation rate. And as your surface grows, then everything actually grows. So like you are actually losing more liters, because it would be sort of stupid to just apply this as a static value over a variable amount of like area. Like as this is increasing, of course, you are losing more cubic meters, but I don't think this is staying the same, because as you're increasing the surface, you're also losing more of this shit too. So hence you should be losing more cubic. Hence the game will never be finished. How do you feel a swimming pool when there is evaporation going on? 2500 to 25. Just fucking basic math. It's stupid. That was like brain fuck. Yeah. Okay, moving on. Engineering. Give me the real deal, man. Can handle it. Hmm. Water temperature. Okay, we are doing the temperature soon. Okay, we actually go by our. We could easily change our stuff to is evaporation coefficient. Is interesting. Okay, the surface area. All here. So, we will have humidity in the game. Could actually create something realistic here. Instead of two values, though, we could just boil it down to one value. The rest has to make sense. If you could satisfy that, water surface area in our case, we may pretend it's the compost surface area, and maybe we'll actually have some factor that actually, when the lid is closed, there is less evaporation. We could actually factor that into, because when the lid is closed, there's going to be less air flowing in. Therefore, V is not accelerating this evaporation. Because the lower the V, the lower the theta value will be, and slower the evaporation will be. So we could do that. What is this hard coded 25 plus 19 though? That's what I don't get. Some magic. What's the deal with temperature though? See anything about Did I miss the temperature here? or the higher the temperature, the humid it gets. So this actually is taken into account. Temperature is not exactly here. There's a 50 by 20 meter swimming pool with a temperature 20. Maximum saturation humidity ratio in the air above the water surface is this. I bet this number is calculated based on this. So then I cannot easily plug in the humidity value that I know. It has to be. I think we could still do that. Let me go to this link. It says any bearing on temperature. It's about mass of dry air, mass of. It's massive. I have to discuss the dinner station, but I'm around. I'm just gonna put the stream on break and I'll be back. Probably half an hour, 45 minutes. Uh-huh. Maximum saturation humidity ratio of air. This is the cool shit. Okay, which has its own equation. So kilogram of water over kilogram of air. This actually makes so much sense because hotter the air, the hotter, like the more water it will carry. So the ratio makes sense. So then you plug that in here. So this is like 20 centimeters is 0.014 something. Something, yeah. So this is actually, this has a formula like this. Which is this shit. Fine. We'll figure it out. Okay. So that's one part of the equation. So it seems we could actually make some progress here. Let me look at this. So this is good. We could bullshit this. V is velocity of air above the water surface. We could also bullshit that too. Because we'll have windy cities and not so windy cities. Which will eventually give us the amount of evaporated water. And how is that helping us? Kind of does. Let's go to our discussions. I want to update the equations page because I just found the hottest or the coolest or the most humid case. Okay, let's read it again. So 20 centimeters, it's this. With air temperature 20, see, that's the thing, water temperature. Okay, sure. Uh, so there's that magical 25 plus 19 again. So if there is wind such that it's half a meters per second, this is the evaporation coefficient. So every hour, theta is hour. Every hour, when you have a square meter of surface, you are evaporating 44.5 kilogram um, of water. Impressive. Seems high, but the area of the pool can be calculated as 1000, so you'll actually multiply it. And then this is that number that we pulled from the other page minus um, for the air temperature is this 50% relative humidity. This actually, I bet, is a, yeah, more equations. Okay, love it. If I read enough equations, I will soon reach nirvana. Bad joke. Anyway, over 300, 3,600. Why is it? Because it's per seconds. This is from this. Now this is making a little bit more sense. In 1 minute, I'm 60. Brain is too old for this. I'm going to sit here. For every minute, okay, this number seemed high, but I think maybe we'll see. It still seemed high by itself, but in this context, it's making sense. Every minute, every minute, if you have an Olympic swimming pool, I think that's what that size. You have 2 kilo, well, almost 3 kilograms of water, well, 3 liters of water evaporated. Like the swimming pool is drinking 3 liters of water per hour. This is actually interesting. If anyone wants to calculate, say, if you want to build a swimming house, a swimming pool in your garden, and then you have to build that system that the water is pumped, so it compensates for the evaporation. So every hour you are feeding into the system 3 liters of water. That's your consumption. So so in a day, if the swimming pool is running, every day you are basically feeding 68 liters of water. So that's a lot of water, man. It's a big swimming pool, mind you. So, and let's not take into account that you have, you know, maybe you have kids and they're jumping in and then splashing water. So that's just, say, look, a calculator. Okay, we have something here. Okay, so what did we say? Let's pretend everything is the same here, right? This is not going to change, let's say, because this by itself is only the wind speed. Fine. This is the surface which we can kind of bullshit. We may pretend that our game world right now is conditions. Okay. Now this is a compost unit. I understand it's not a swimming pool. So this part and this part doesn't kind of make sense. But let's say it does. So the only thing we have to change here is that this actually has to be, let's say we have 2 by 2, five square meters. So we'll actually divide this in 200. Okay, this is per second, per minute, per hour. Okay, this is it. Per hour we are using 0.84. That's the value we have to feed in here. Or let's say 85 because this is actually up 85. Now this is looking scary because it's too steep now, right? So when you have 150 liters of water and you are losing 850 milliliters of water every hour, uh, in about 4 hours or like hours, this is too steep. My math was correct, but this is thinking that you have an open surface and evaporation is high. Need to adjust this equation so that so this helped definitely. One thing that kind of doesn't make sense here is this. It starts with seconds, then it actually goes to hours, which means this just feels too high to me. And then, because here both equations have the theta that I understand. Here it's calculated by the hour. And then here they are plugging in the second value and then just automatically converting it to hour. That part doesn't make sense. This by itself is 34 point half. Okay, I need to break this down. It's really not making sense. The numbers do, the unit doesn't do. How did you get from meter per second to kilogram per meter? Evaporation coefficient. So altogether, this is whatever that value is automatically constant. Okay, call it horse shit, but So by doing this 5 square meters, that this is that humidity value. So in my case, what I did was it was still too high. So did we say like where were we? We said every hour it loses 2.82 liters of water for swimming pool, right? That was for a surface of 100 square meters. What are you doing? So we said divide this. Actually, no, that's not what we did. Let's do it this way because we didn't actually do it for the hour. We did it actually has to be multiple 60 here. You can either do it that way or yeah, well, this kind of checks out somewhere. Let's do it again from here. If for 1,000 square meters, every second it's evaporating this much. Every hour it's evaporating this much. That's a lot of water every hour. Because before I actually did that was every minute. Yeah, even that seemed too much. This is also a lot of water. And then this is the number we got to, which was correct. Still seemed too high. For our compost, every hour is losing almost a liter of water. So the part that doesn't make much sense to me is this is the first hour ish. Here's the problem though. My equation is decay function. Their equation is a linear one. It assumes that every hour it's losing the same amount of water, which is 169. It never considers it as I suppose I'll either keep my own equation and fudge the numbers, or if I'm going to go with their equation, then it has to turn into a linear equation, which means we cannot really use this equation. Like this part has to change to the linear one, so that this actually has to be minus, let's write an alternative function here. Okay, let's make this. Let's create another w function here. Let's call that w new, like w, where are you? Okay, this is going to be minus 0.85, and we still need to do this. We are assuming we are adding half a liter of water every hour when the lid is on. Say, sorry, off. And here it is. And of course, kind of started 100 and so we are actually okay with oxygen. Let's hide that. So the blue line is our exotic function, also known as decay function here. This one, the purple one, is the super scientific evaporation calculator, which then has this linear decay. So in the first hour, zoom in a bit. Well, if we are losing in 10 hours, we are going to lose 8.5, which is going to be 1.5 right there. Okay. Now this value, I mean this graphic and the other one are still separate from the other concept that we did here, the minimum and maximum threshold. It still has to apply. Like has to be between certain values. But here's an interpretation of this. In 20 hours, we hit the rock bottom with the K function. Like it's decaying very quickly. It's 0.2. Okay. And as you increase the decay number here, you're actually decaying it faster. Let's get this back to 2. With the linear one, after 20 hours, we are still in the safe zone because remember, we have this magic 125 area. It's like, because the min is 100, the maximum is 200. We said 25% edges, like from the edges, usually speaking, zoom in a bit. 25%, 25%, they are danger zone. The middle 50% is the safe zone. When you have the minimum 100, maximum 200, 125 is where your danger zone starts. So we're essentially checking when we reach the 125 danger zone. So we need roughly 29 hours, 8 hours with the linear. Okay, okay, and we get to the danger zone in around 9 hours. I must say I actually like the scientific better. From 2 reference points. One, I don't think in real life I water my compost every 9 hours. Now these values are a bit arbitrary, but at least they are consistent in this game world. Okay, it takes it's as if it takes a few days to actually water your compost, which fits the scientific model. Second part is from the player perspective. Since it's a game, yes, we want to give plenty of things to do for the player. The player will be busy planning other things. They wouldn't want to necessarily keep remembering to water compost every 9 hours because we don't want to turn this game into. Of course, this is the rain part. We can actually incorporate that too, but can we fudge this number? It's the key function so that it resembles more. I think the best way to do that is sort of like which then kind of turns into a desperate attempt, right? For the sake of make this two and then this. Down way. So in the scientific model, every day you have to water. I'm gonna get down to 5. This is of course taking into account that actually no, this is still okay. This is not raining. We are not adding any more water. It's just a normal decay. So every day you have to, every 30 hours. Whereas with this, it's close to 20 hours. Part of me still wants to keep that wave function. Now that we fudge the numbers to feel a bit more close to the real. How fast is the time in game versus um, good question. I think right now, I think every real second is a real second in the game, but I think we did it like every real second it was 5 or 6 game seconds. There's the speed factor here. It's incrementing 15 seconds when it's on speed mode 2. This is actually adding 25 seconds, but in normal mode, I think it was 5 or 6. We may have changed it at some point for testing purpose. Yeah, but you're not going to wait. It's going to be a bit faster, of course. Won't be 1 to 1. But you can always do this too. A day, a few hours, sort of thing. Actually, when you push it that far, it's you push it 1 day or 2 days, 3 days. It's growing. That's good. One more day from flower state, it's gonna go to green parts. One more day will be red, or like yellow. You wait too long. Of course, these values will change. Now they won't be all 1 day. Will die. And at this point, you can compost it. That's what actually I'm working out. And we compost it to this one. We are deciding this ratio. This is the stuff we did today in conjunction with this value. We are now figuring out this water. So that this value here could be either decomposing or stagnant, depending on different factors. But I think you were already watching that. I did the stream. I might be repeating myself. Let's not forget that this is still going to need some temperature. This is going to affect. Because if we are doing this, okay, we are doing this, which gave us this value, which we sort of arbitrarily put here. And we may assume that these two functions are closely related, except when it's raining. Okay. Here we may assume that although they are kind of close and they are actually diverging here, this is like basically a week, like 6, 7 days. So for the player to notice this kind of discrepancy, they will fast forward the time more than 7 days, and at that point, stuff is not going to make any sense. But in this case, there is still going to be some room with the decay function, so things will look a little bit better. But with the linear decay, it's going to hit zero around 6 7 days. That's more drastic. That's why I kind of want to go with the decay. And if they naturally play the game at a normal speed and they actually spend 1 week game time, it's much more likely that they are going to take some action to push these numbers around. So then it's as if this equation is going to reset itself and it's going to have a new start point and new decay pattern. It would be like changing this part, adding water artificially, like through here or. So I'm not too worried about these two diverging here. I I think real need at this point is that if I could find an equation by myself, which is this blue one, looking close enough to the scientific model, um, within a certain time frame that is acceptable by the player, so they don't notice this divergence. But I'm streaming about it now; everybody knows. So you get my point. Gameplay wise, players don't notice that. That's okay. Now the complicated part, yeah, this is actually good, but here's where things kind of go a little bit crazy. They are still okay, maybe within first 100 hours, but this is a scarier scenario than the other. This is like I'm basically simulating rain here by turning closing the lid or opening the lid. Because when the lid is off, even if it's raining, you're not getting any water back. So L and R has to be 1 so that you are adding half a liter of water every hour. So when these two equations start to diverge is around 100 hours. That is still pretty much the same case. Around 100 hours, they are diverging. The interpretation is though a little bit more severe. In the raining case with the scientific method, when the water content hits zero, you are basically spending 420 hours. That's 3 weeks. And that is given the fact that it's raining for 3 weeks and you haven't closed the lid. You are still losing water, so like you're losing water even though you are adding half a liter of water. So, mind you, this number was bullshit, but I mean, the reason why this makes sense that starting at 150, if you are losing 850 milliliters of water and adding 500 milliliters water, you're essentially in the end losing 350 milliliters. Of course, you are going to hit zero. You're just going to hit it a few weeks later instead of like the first, you know, after a week. It'll take 2 more weeks. Whereas this one has this funny interpretation that at some point the water that is getting into the compost unit is compensating for the evaporation, that the compost unit will actually get more and more wet, and if you don't close the lid, or if the rain doesn't stop, this is actually going to go to infinity. And that part actually makes much more sense to me, feeling wise, because I mean, it's unrealistic that it will rain for 3 weeks straight. But hey, if it did, and if you didn't put the lid on, I think it makes some sense that, gonna be wet. That's why I will leave these two equations here for now. I will try to incorporate the temperature stuff. Now the temperature stuff is also interesting because it already played a part in this 0.85. Now, if I'm going to include the temperature stuff, it's as if I should already be writing these equations so that I get to this 0.85, not by typing it here, but through some other calculation here. Let's save this bad boy. Also, around 10 minutes, I might be called to dinner. Maybe I'll actually stream after dinner because I feel really excited about this. But I can't promise. Maybe there will be another stream tonight, but maybe not. So let's try to write this somewhere. Let's go by hour, which is sort of like theta. Theta is this. Um, Velocity of air above the water surface. I wish there was a way to group these things and sort of close folder. Okay, constants. Overview. Awesome. Only two more. Love it, love it, love it. We need a constant, which is let's remove one. I think I could just do it. Velocity is 5. Can only be 0. So then we have theta. Let's actually write that in a smart way. Not this shit. This. I thought we had theta somewhere. Theta reaching here. Do you remember theta somewhere? And is pi. Okay, so we'll call this what? What is the official evaporation coefficient? Let's call it E. Evaporation, of course, E will be this. I don't think it will allow us to put E. Maybe it will be like this, 5. And can you actually do 5? No. Let's go E. Let's do some kind of X. Okay. We know that I doesn't. When V is 5, this is 95 plus 25, it's 120. However, in terms of calculation, that doesn't check out because when I said 5, why did I say 5? Variable is it's 0.5. What was I thinking? Just 0.5. So that's 38. Sorry, what? 34 and a half. Okay. That's something there. That's theta. So then we have the square meter part here, surface area. And that will be the surface area of the compost. We can actually pull that from here. Okay, I arbitrarily set it as 5 square meters. It's like, I don't know, 2 by something. 2 by 2 is 4. Let's make it 5. Okay, that's that. Because we will have the dimensions here. Whatever this 5 inches. Centimeter. This is, yeah, 4 square meters. Um, Surface S, 4 square meters. I think the dinner is here. Yeah, I think I will really try my best to continue to dinner, but I'm going to conclude here just in case, because if I put the stream on break and if I don't show up, it'll look stupid. So for the time being,